Okay, can you hear me now?
Yeah.
Okay. Yeah, so the initial motivation was, like, in most, I guess, like modern enumerative geometry problems, it's about, physicists would say just like supersymmetric localization of 3D n equals 4 gauge theories. If you don't know what one of those is, there's at least one of these for every, you can think of them associated to framed quivers. There's more of those than just ones that come from quivers, but this is fine. And so at this level, it could be totally arbitrary quiver, doesn't really matter. Have some self loops, whatever. And interesting thing to study is like supersymmetric partition function on some geometry. So this is three-dimensional, so you take its partition function on 3 manifolds. And so if you take partition function on something like Riemann surface times circle, this kind of reduces to some kind of count of maps from whatever Riemann surface is into some target, where the target is what's called Higgs branch of this thing. And for a quiver gauge theory, it would be like the Nakajima variety associated to whatever quiver you have. And more precisely, what you mean by count is, if I specialize to the case where actually space, so this would be like C. So to actually do counts from higher genus curve is not a very good thing if you want actual formulas. So usually what you're interested in, some kind of local version of this, where you take C to be like a sphere, or P1, and you work equivariantly with respect to some automorphism rotating P1. Then the partition function on this kind of geometry, I'll say CQ, times S1 is some kind of Euler characteristic of something called virtual structure sheaf or symmetrized virtual structure sheaf over some kind of appropriately defined moduli space of holomorphic maps from P1 into your target. And so to say this precisely, you have to take some compactification of this thing so that whatever you're computing is reasonably well defined. And the one I will be working with today is called Quasimap. And I'll define it later in the talk, but the point is it's just some compactification of moduli holomorphic map. And so you can learn a bunch of like interesting stuff about the physics of 3D n equal 4 gauge theories by studying these kind of counts, working equivariantly with respect to all symmetries of the problem. But as is very well known, there's more to life in 3D n equals 4 gauge theories than just the Higgs branches. So 3D n equal 4 theories also have Coulomb branches. And for these kind of quiver gauge theories, which I didn't really fully define, but just said what they are, or at least that they're labeled by quivers, this could be determined by like the Braverman-Finkelberg-Nakajima definition. So I'll just say defined by these guys. And so some kind of general question one might be interested in is, given that Higgs and Coulomb branches come from kind of the same thing, how do you directly connect Coulomb branches to enumerative questions? And so I am like hardly the first person to ask this question. There are like existing, so some like previously existing things. So it's just like previous proposals. One is elliptic stable envelope. And these are, the relation to Higgs and Coulomb branch is, these just give explicit relation between counts to x and to x check whenever they're both defined. And some other idea is that the quantized, so because you have 3D n equals 4 supersymmetry, both Higgs and Coulomb branches are in particular holomorphic symplectic, so you can deformation quantize them. And there's some kind of meta conjecture or picture that quantized Coulomb branches should act on some kind of cohomology of these moduli spaces and maps. It should be critical equivariant, whatever. So I'm going to tell you basically a third thing in the list, which is a little bit different. It's closely related to things our very own Telemann has been saying for some time. But the kind of origin of the question for me was just rethinking, if you wanted to explain to like actual physicists why this thing confused the Coulomb branch, how do you tell them? And so I'll begin by sort of explaining that, and then this will lead us to, it'll be some computation, and then we'll generalize this computation to get some picture of how Coulomb branches will interact with some kind of enumerative question. It won't actually, so this is the counting K theory. Today I'm just going to actually be interested in cohomological questions, but everything I say will have some K theoretic analog. Yeah.
So when you say previous proposal,
yeah. Mm-hmm.
What does it actually X and Coulomb branch or Higgs branch?
Well, X and X check are just a pair of Higgs and Coulomb branches. So my convention, X was Higgs branch, X check was Coulomb branch. And in some nice cases, those will actually both be Nakajima varieties. They'll just be different ones. And the elliptic stable envelopes, I don't want to like go define them because this will be some aside, but like you can use them to just explicitly give formulas that express like the counts of this in terms of the counts.
If you're C, right? Then you expect that whichever computation do you in terms of Higgs branch, there should be an equivalent computation in terms of Coulomb. If it's just because the theory doesn't pick a phase. So the envelope story is a way of describing that if you take C to be a disk with suitable boundaries, and it tells you like which boundaries you can compare. So that analogous thing, so you can classify this by boundary.
Yeah. Yeah. And in order to, I'd realize what I've said might create artificial confusion, so I want to correct it now. These two things are really about pairs of Higgs and Coulomb branches. They really both work when you know the Higgs and the Coulomb branch in like reasonably explicit terms. And it's about Higgs and Coulomb branches of the same theory. What I'm going to say today is not about Higgs and Coulomb branches of the same theory. It's about Coulomb branches of some theories and some targets that are not Higgs branches. Okay, so that's a difference between the first and second thing and the third one. Okay, so let me start by just saying, going back to what I said was kind of initial motivation for me, which was how do you actually explain along the sort of same set of arguments which leads to this statement, why the Coulomb branch is what it is. So whenever you do computations in the Coulomb phase of anything, it's always most natural to start with the pure gauge theory, because that is the simplest possible thing that will have the Coulomb phase. So now I'm going to consider pure, I'll just say UK, 3D n equals 4 gauge theory. And I'm going to sketch out what for a physicist would be the localization argument for the path integral of this theory. And for math, if you're from math, I'm just going to tell you a recipe of if a physicist says compute this thing, this is what they really mean by compute that thing. So field content of this thing, since it's 3D gauge theory, you can put it on 3 manifold. And for some technical stuff, like I'll strictly be considering it in some topologically twisted, I'll strictly be considering some topologically twisted version of the theory, what's usually now called the 3D A model. Topological twist, the most, I think, coordinate independent way to say what this is just the dimensional reduction of the Donaldson-Witten twist in 4 dimensions. Field content of this thing, what is it? It's just, you've got, well, a gauge field, hopefully. I'll say bosonic field content. So this is just gauge field. This is the real adjoint scalar. And there's also some complex adjoint scalar. So in some kind of, you really can combine these into a triplet of some R symmetry, but I won't do that. So I'm also never going to consider this thing on like general 3 manifold or whatever. For me, this will always just be R2 times interval. And I'm going to think of this as C. So my coordinate on C is Z, and my coordinate on interval is T. And then just like very general principles thing, partition functions on something like 2 manifold times S1 always computes traces. Partition function on something like 2 manifold times interval computes like matrix elements. Right? So what we expect for the answers is that they can be interpreted as somehow some matrix elements where the thing you're computing looks like some kind of t equals 1, something that comes from the t equals 1 boundary. You put some observable in the middle, and then you have something from the t equals 0 boundary. And the rest of what I'm going to say for the next several minutes is just going to be saying like what does that actually mean. And of course, it also goes without saying, just like I always want to work equivariantly with respect to everything over here, I will be working equivariantly with respect to rotations of this thing, and I call the parameter epsilon. So if you want to actually compute like path integral of the theory on this type of geometry, you have to just give some kind of boundary conditions on the t equals 0 and 1 ends, and then you have to say basically what is the localization locus to, so let me take a few steps back. Up there, I was saying, well, the partition function of the physical theory, whatever it is going to reduce to some kind of more finite thing, which is like an integral over some space of holomorphic maps. And so the idea is that, the holomorphic condition on maps is like some, special supersymmetry preserving condition, which picks out a much smaller subspace of the space in all fields. And so likewise, if you want to apply the same kind of argument here, you need to figure out which subspace you're going to collapse to in the space of all, these guys plus fermions, blah, blah, blah. So I won't, because the audience is a lot of mathematicians, I won't review like the full gory details of how this goes. But the important part is that the localization locus for this thing is just, well, you can guess if you already know it's dimensional reduction of Donaldson twist. So the Donaldson theory is about the integral of something over instanton moduli spaces. If you dimensionally reduce the instanton equations, they're just these things, the monopole equations. So you just look at solutions of these up to some gauge transformation. So the idea is then you're going to get some kind of formula for this thing in terms of integrals over some kind of space of supersymmetric configurations. So some kind of moduli space of solutions to these. And then all the other stuff tells you some kind of cohomology class on that thing. This is the general pattern for every computation like this. Yep. It's a very nice exercise to do, but it will be kind of orthogonal to everything else I'm going to say, so I don't think I'll have time. If you want to see it worked in the like Donaldson theory example, there's a paper by Atiyah and Jeffrey from like early 90s that will just kind of do it. So like what I'm doing is like I'm basically just like copying and pasting the Atiyah-Jeffrey argument to this situation. So yeah, that's nice. In one sentence, the idea is like whenever you have supersymmetric theory, well not whenever, but like for suitably nice supersymmetric theories like this one, when you have these topological twists, you can interpret the twisted supercharge as some kind of like differential and some kind of de Rham type model for cohomology on space fields. And then by just doing a bunch of like formal arguments that would be like literally true for finite dimensional smooth targets or smooth spaces of integration, you argue that this infinite dimensional looking thing is actually some kind of cohomological representation for a finite dimensional integral. That's how it goes. And yeah, so it's a nice, it's a very nice story, but it's too many details for now. So instead, what I'll do is I'll just say, like, assuming you've already done all that, what is the output? So what is the space of supersymmetric configurations? What kind of class is going to integrate? Yeah.
When we do this whole thing, there might be fermionic.
Yeah, exactly. And so the fermions, like their role is they just organize into the whole cohomological structure. They just kind of go along for the ride and everything. So like, yeah, anyway. Okay, well, to tell you what's the actual space of solutions, I have to pick some reasonable boundary conditions on either end. So the boundary conditions I want to consider were actually first studied by Kapustin and Witten when they were trying to give some account of geometric Satake isomorphism from a gauge theory point of view. And well, they're just that if you take the connection and you restrict it to the t equals 0 boundary, it's just 0, so that's Dirichlet boundary condition. This equation tells you what the other boundary condition has to be. If you contract with the normal, this had better be 0 at the t equals 0 boundary. And then you put kind of the dual boundary condition at the other end. So you say that if you contract with dt fa and restrict to t equals 1, that's 0. And vice versa, sigma restricted to t equals 1 is now 0. And there is something I should tell you about phi, but since everything that goes on with the actual moduli space solutions is about A and sigma, I will just write things for them. So something which is now very easy to show is that if this is really all you're doing, you just look at solutions to this. Oh, and I should say one more thing, sorry. Because you actually fixed the connection to something at the t equals 0 boundary, you now want to divide only by the gauge transformations. You want to divide only by the gauge transformations trivial at the t equals 1 boundary. Sorry, t equals 0 boundary. Just because, like, here I want to think of this as like I'm actually giving you a bundle, not just like isomorphism class of bundles, but like fixed bundle. And so what's very easy to show is that with this list of stuff, solving those equations, only solution is actually trivial. So the space of configurations is a point. So what I wrote up there is SUSY. Configurations is really just a point. And the proof is like pretty easy. You just take this thing, and then you can take it the norm square and integrate that. You integrate by parts, you can forget all the boundary terms. And this means that by some positivity, this and that have to vanish separately, which just basically means that A and sigma are both constant. But if there's 0 at either end and constant, then 0 everywhere. So what this means is that if you want to get any kind of interesting like output from this kind of problem, you have to like break that argument. So the easiest way to break that argument is to put some kind of singularity condition on the fields in the middle, because then if you try to norm square and integrate, it doesn't work. So this tells you basically which observables to insert. So to get around only integrating over points, you have to insert some observables. And so now I'll actually draw a picture. So our space-time is just this kind of like sandwich thing, where this is the t direction. And I'm going to put some kind of like point-like insertion somewhere in the middle here, because I want to work equivariantly with respect to the rotations. That had better be at the origin of the R2. What is the observable? Well, what it does is it changes the class of fields over which you integrate. Instead of looking at smooth solutions to the equation, you look at fields with some kind of prescribed singularity. So to describe what is the singularity, so this determine some singularity. What is the singularity? You pick a dominant co-character from, I guess, C star into GLK. Well, in principle, the complexified gauge group, for me, this is just GLK. And I'll say mu is its derivative at identity. And then you pick some kind of local coordinate system here. And so if you write like r theta and phi, our local spherical coordinates, about the insertion point, you just impose the kind of standard, what's called Dirac singularity in the field. So like if you like retrace this to the elementary physics notation, this like literally is the potential for the Dirac monopole charge mu. Okay, so I put some kind of singularity on the fields. That's the main point. And that singularity depends on choice of dominant co-character. Okay. So this gives the space of solutions the chance of not being boring. So now what actually is it? Well, as usual, if you actually want to describe the space of solutions to something, you had better do it in some algebraic geometry model. So yeah. Yeah. You would say we're inserting some kind of observable that changes the localization locus. Yeah. Now, how does it change the localization locus? Well, the idea is if you just write this stuff in coordinates, which unfortunately I think I just erased. So t is the coordinate in the interval direction, z is the coordinate along R2, viewed as c. Then what they are is you get some equation like the covariant derivative in the t direction plus I sigma commutes with dz bar. And then some other equation which is just like some, you can view as the real moment map for whatever quotient you're doing by gauge transformation. This is like the usual stuff. And so then, as usual, I want to just forget this thing and divide by the complexified gauge transformations. Yeah. Oh, right. So what I'm doing here is some kind of like a Kobayashi-Hitchin or symplectic equals GIT thing, where you say if I've got some kind of like real symplectic quotient, then like under some set of assumptions, it is like slightly non-trivial here because it's infinite dimensional. Then looking at the space of solutions to the real moment map condition mod the compact, maximal compact in the group is the same as looking at just everything without the real moment map mod the complexification of the gauge group. Usually there's some kind of stability issue that enters here if you want to compare quotients by like complex reductive group versus the maximal compact. It actually turns out because of the boundary condition here, everything is stable, so it's okay. But the slogan is that like, you know, real moment map here is like some nonlinear PDE, very bad, very hard. But if we just pass to being happy about knowing what is localization, locus is a complex manifold, we can say some stuff. Okay. And now, like, what does this equation actually say if you're working up to the complexified gauge transformation? It says something very, very easy. Some like very basic rewriting of it is this. It just says, you know, at each fixed time slice, you've got some d bar operator on, you know, the gauge bundle restricted to that time slice. In complex dimension 1, there's like no integrability condition on d bar operator, so that just defines it as a holomorphic bundle, right? This just says that if you vary in time, this thing only changes by a complexified gauge transformation generated by the other fields. So in other words, if you work just up isomorphism of holomorphic bundles, doesn't change at all. Okay. So what this basically says is that as a holomorphic bundle, I'll call E the gauge bundle since we're in since gauge group is UK. This is just some rank K vector bundle. E restricted to the time slice is, I'll just say constant in T away from the singularities. So in particular, this gives you another way to see why the space of solutions came out as a point when we had no singularity, because that just says at T equals 0, you tell me a holomorphic bundle, and then it just doesn't do anything. And it is whatever it is at T equals 1. So there's just no moduli associated to that at all. But now you can see the basic thing that's going to happen is whenever you introduce this kind of singularity, there actually is the hope for some kind of jumping behavior. And the whole moduli space of solution is just going to be like encaptured by whatever is that jumping behavior. And so what is the jumping behavior? Okay. So the picture to have in mind is like, here's some piece of the t-axis. There's some kind of singularity. Yeah.
How you see that this is consistent with the boundary conditions you went for, so that indeed you actually get a point.
Yeah. It's because, and I just erased them very unfortunately. The boundary conditions, the important part of them was that I had picked A to be 0 at the t equals 0 boundary. So what that says is that like my initial holomorphic bundle is just trivial. And you can think of it as trivial bundle on C or trivial frame bundle on P1, of course, like same. And then the boundary condition at the other end was just Neumann condition, which just says like you don't impose any condition on the gauge field. Then like what the complexified equation, like what the holomorphic part of the equation says is just you start from the trivial bundle, it evolves, and it just is what it is. And then, so clearly there's only one, it's just one possible evolution up to gauge transformation. Right. So now if you actually have some jumping, you have to say what is the jumping? And so what this means is you have some E, which I'll just call E0. On this side, you can think of this as the framed bundle. If we're doing any gauge group, it would be framed GC bundle on P1. Framed means you just fix some trivialization at infinity. And then it just becomes some E1. And now you want to say, if I know that E0 is just trivial, so this is like fixed and trivial, what is E1? Well, what is any bundle on P1? You can describe it just by giving a transition function, g of z, which you just think of as the GC valued function on, I'll just say C with the origin deleted. And if you were looking at really just all bundles on P1 up to equivalence, you would take a quotient on the right and the left by, essentially just the gauge transformations, which are regular at 0 and regular at infinity. Here, since I'm working on C and I fixed some trivialization there, I'm only going to take the quotient, let's say, on the right, because I consider trivialization at infinity is just fixed. Okay? So it's this up to this, where this is regular at 0. Okay. And so now it's just some elementary calculation. You can show that if you put the Dirac singularity there of charge mu, well, what was mu? It was basically co-character. The Dirac singularity forces g of z to go like something regular times z to the mu as z goes to 0. But okay, now like everybody in math here probably realizes exactly what I'm describing. It's just some kind of like Schubert cell in the affine Grassmannian, basically. So, some words for this thing. You can consider affine Grassmannian. So I'll say GCK is just like all the Laurent series in Z valued in GC. GCO is like all the formal power series. Affine Grassmannian is by definition GCK mod GCO. So this is just like basically what I've written there, up to some minor details that work themselves out. And the moduli of solutions, or if you like the localization locus, is really just, if you take the quotient on the right by GCO, then of course it still acts on the left. And you get some orbit here inside of G, and this is like well known. These things are finite dimensional and reasonably nice spaces. So I'll also mention like what I've basically given here is some kind of like differential geometric or gauge theoretic realization. Well, Kapustin and Witten did it. I'm just calling it realization of these spaces, and so a bunch of stuff that's actually known in the context of affine Grassmannian you can like reprove this way, but I won't do that because I don't want to get off track. But something which is maybe worth pointing out is that this is usually not compact, but it is compact basically if and only if mu is minuscule. And I will be restricting myself to just minuscule case throughout just to avoid artificial complications. Yeah, and so maybe it was worth writing one example of what this is. So remember we were in just some GL, so you can pick just the defining co-weight. This is also called ger mu sometimes. Then in this case, ger is equal to its closure, and they're both just projective space. It's easy to understand why it's projective space. It's because like, what were we actually doing? We were just modifying a bundle at a point here, and the choice of the reason you get a projective space is because saying that you want to do the modification of type mu means that you're basically just making a singular gauge transformation that's like z. And so what you need to do is just pick some line in the fiber over 0 to say I want to multiply that direction by z. And so the space of choice is this direction. It's just a projective space. Yeah, okay. So this is some review of what is the localization locus. Now I'm almost done telling you how to compute things. I just have to, so I've told you the integration domain, and now I have to tell you the kind of stuff that can appear in the integrand. And if any of you know the Donaldson theory story, it's basically exactly the same. So I had said that in reality, this theory had the bosonic fields was like all of these things. And I skipped many details, but the point was the localization locus was determined by A and sigma, and I told you phi I'm going to like mostly sweep under the rug, so now I'm going to pull it back out from under the rug. And what does it end up doing? Well, just as some immediate consequence of the supersymmetry algebra, some class of supersymmetric observables, which become like cohomology classes, on the moduli space, is just gauge invariant polynomials. Into phi, evaluated at some point. So if I want to preserve this rotation symmetry, then I'm going to be turning on equivariance with respect to. That point had better have z coordinate 0, and t coordinate is just something. In fact, for me, it'll be fine to just consider t as 1. So we'll just look at. So picture to have in mind for what you're computing is you've got some stuff. And t equals 0 boundary is here, t equals 1 boundary is here. You have some polynomial in phi, which you put here. Maybe I'll call it f, or whatever. And then somewhere in the middle, we put the Dirac singularity of charge mu, which I take to be some minuscule colloid. Okay, so now which cohomology class it determines for you? Well, it's easy to say what it is. So anytime you've got any space, which is like the moduli space of solutions to some kind of gauge theory problem, you can always do this kind of universal bundle construction, which just means that, like, if I call this M, and of course it's really just M bar, it's really just this orbit in the affine Grassmannian, but viewed as a moduli space of solution to some equations. The point is you can form a universal bundle, which I'll call curly E, over M bar times the space-time. And the construction of it is totally tautological. You just say, well, its fiber over a point is the fiber of whatever bundle corresponds to the point in the moduli space that you're at, and whatever the fiber of that bundle is over the corresponding point in space-time. It's a universal bundle thing. And then these just correspond under this to just the characteristic classes of E, and I'll say E restricted at z equals 0, t equals 1. Right. So if you restrict it in this factor, you get some bundle over the moduli space. You can take characteristic classes of that bundle. So I'll write those just P of E.
Sorry.
Yeah.
At some point, I lost track of some of the
Uh-huh.
So we started out with this like pure 3D gauge theory.
Sure.
All right. So how do we end up with so this E? It's like I guess like the frame bundle of the bundle solutions.
Yeah, it's just the gauge bundle, right?
Okay.
Yeah.
I guess how do we end up with the bundle on P1? We look at this like.
Right. So I pushed under the rug that since I was looking at solutions to equations on interval times R2 or interval times C, but in order for like various things I said to actually be true, you need to also impose some like decay conditions on everything at infinity of C, including the gauge transformations. And when you do that, that means that you can that means that near infinity of R2 they've got fixed trivialization, so you can just view them as a bundle on P1 that's framed. It's a similar thing, like maybe a slightly more well-known thing is like if you're doing like four-dimensional instantons, you can, if you have four-dimensional instantons on R4 which are framed, you can view them as like holomorphic bundles on P2 which are framed over the line at infinity. And it's the same type of thing. Right.
So
yeah.
When you say Suzy observables,
Uh-huh.
so are the only observables which are like supersymmetric ones that are even very quantity over this?
No, like in principle, the Dirac singularities I put were also supersymmetric observables. The argument for that, anyway, I don't want to get like bogged in physics detail, but like I'm just saying a particularly nice class of them that I want to consider is this. Okay. Yeah.
Okay, related question.
Yeah.
So what determines the fiber of the E? Your choice? Or is that
The fiber? I mean, E is determined as this. Yeah, I mean, it's just E is determined by solving the equations, right?
I thought you have a pure gauge theory.
Uh-huh.
Just specify a principal GLK.
Yeah, it's a GLK, so it's GLK, principal GLK bundle, same as rank K vector bundle. That's it. I'm just viewing it as the rank K vector bundle. Yeah. Yeah.
What is pure?
Oh yeah. Pure just meant that I didn't have any matter fields. It meant that I only had the 3D n equals 4 vector multiplet.
Maybe just draw the quiver.
Oh yeah. Oh God, I'm so sorry. I didn't draw the quiver. Yeah. So the quiver for this thing is just like one circle node with K in it. So if you had matter, it would have a box node. If you have no matter, it's just a circle node. Okay, yeah, sorry. So like in particular, this is a nice example for if you really just want to think about Coulomb branch, because the Nakajima variety for that is empty, but it still has a very interesting Coulomb branch. Right. So, but you see now I've basically told you how to compute path integrals of this kind. They just reduce this, like, so the partition function with this data is just equal to the integral over some ger mu of this characteristic class of the universal bond. And I should say this integral is taken in GC times U1 epsilon equivariant cohomology. And so it's clear that everything in sight was rotation equivariant. To get to how does GC act, unfortunately, I think I erased it again. But remember, we're only divided by the gauge transformations that were trivial. At t is 0. So that means that like gauge transformations which are just not trivial there continue to act on the space of solutions. This gives you the group action. And in fact, if you were doing like physics style explanation of this computation, the boundary value of the field phi at t equals 0 would just tell you what are the equivariant variables for that. Okay. So now, if you notice, I said this thing was like, right. So I'll just give you like one example of what a computation with this looks like, because it's like super duper easy. And then it will be so easy that clearly you have to do something more interesting to have anything worth saying. So then I'll tell you the more interesting thing. Okay. So as some very explicit example, you can pick mu to just be, once again, this fundamental guy. And like, what is the gauge invariant polynomial in this case? Like it's really just the same. So the gauge invariant thing, I can equivalently think of as just like the function of the Chern roots, or just some function f of like k variables, which I call phi I. So phi I is 1 to k, and this is the sk invariant function. So what is value of this integral? Well, remember here, GER was just the projective space. And so you're really just integrating over a projective space, and we're doing some in equivariant cohomology. The G action is just the obvious one on the projective space. And so the integral you can just do explicitly by localization. You sum over the fixed points. The weights sort of are what they always are. So this is just localization weight. And this thing, well, like you just have to ask what are the weights of the maximal torus of that in the fiber of the universal bundle at that point at a torus fixed point in pk minus 1. Well, the torus fixed points in pk minus 1 are just the coordinate lines. And what this thing tells you, like thinking of this pk minus 1 is really a GER, it tells you that you've chosen to like Hecke modify your bundle on the spatial slice by just like multiplying by z along that coordinate direction relative to whatever trivialization you originally chose. So if you just spell out whatever this means, it means that the ith variable in f gets shifted by epsilon, where epsilon is your equivariant variable for whatever, for the rotations. And so this is just like explicitly divided this out. Okay, you can very easily generalize this computation to do what's called address monopole operators. It just means that, well, the projective space has the rank k minus 1 tautological bundle over it. So in particular, I can just cup this thing with the tautological, with the Chern polynomial of the tautological. So I'm generating variable x. What does that do? Well, over here, it just changes the pure denominator to have some numerator. And it looks like that. So this is just really just localization's formula spelled out for this thing. Okay. And now the point is that you can view this entire expression as really just the original f thought of as a symmetric function of some variables acted on from the right by some difference operator. That looks like that. And I'll call this thing for future reference like u plus of x. Yeah.
Sure. So the curly E is the bundle
over the moduli space, yeah. When I've restricted it there. Yeah. And so I'm just computing explicitly some like, so if you take some characteristic class of it, that's a equivariant cohomology class. So you can evaluate its integrals involving that by localization.
What is the variable x?
X is just some generating parameter for the Chern polynomial. Yeah. Okay. So maybe I'll write this. So yeah. Okay. And so the point here is that like this construction basically tells you how to trade a difference operator for a space. because whereas you could have just said as a statement on functions, I consider acting with some operators look like that, you can geometrize the whole procedure by saying I view it as the characteristic class on some space and integrate over the space. Okay. There's also a cousin of this, so I'll call this mu plus. You could have done the anti-fundamental co-weight, and you would have gotten u minus, which is basically the same formula, but I'll still write it. There's now a plus sign in the exponent, and the sign on the sign of the weights in the tangent space flips. Okay. But same procedure, and of course, I mean, it's easy to convince yourself. If you consider just arbitrary fundamental co-weight for GLK, you'll just get some integral over a finite dimensional Grassmannian, which you can make totally explicit by fixed point formula. Okay. So the main conclusion here is that if you just study the pure 3D equal 4 gauge theory on this very specific geometry of just R2 times interval with some specific choice of boundary conditions, the whole business of computing path integrals with insertions of observables reduces to some very explicit operators acting on some very explicit functions. Okay. And so for those of you who kind of know already the Braverman, Finkelberg, Nakajima story, like you can recognize that this basically is the action of the quantized Coulomb branch of the pure gauge theory in one of the modules that is defined tautologically by virtue of the fact that you define it by some convolution algebra. And the only thing to check, which is very easy to check, is that you can ask what happens if I insert more than one Dirac singularity in the bulk. What happens is the localization locus changes, and I don't want to go into like, so this will probably be the kind of remark where if you know the word that I'm saying, you already know what it is. If you don't, just don't worry about it. Like you just replace this by the convolution of several orbits if you have several singularities, and then it's very basic to check that localization against that thing exactly matches composition of difference operators here. So you just geometrize the whole procedure of acting with these difference operators. Okay, so now I will almost move on. I just have to review maybe one thing before I move on. I kind of already said in words what I'm about to say, but I'll just make it totally explicit. So to say it a little bit more sharply, if you consider this polynomial in x in the equivariant variables, as well as the two guys u plus minus that I just defined, these really generate the quantized Coulomb branch of the pure gauge theory, which if you want to think of it as associated to a quiver, is this thing as defined by BFN. Okay. And so like if you were to take some epsilon to 0, like classical limit where this is just the ordinary Coulomb branch like as a space, the way you would organize this information is you would say, well, I have something called the scattering matrix, which is just a collection of polynomials. It's a matrix of polynomials where Q is monic of degree k, and then the U's just have degree at most k minus 1. And you impose that the determinant of this is 1, and that basically fixes Q tilde. And so this is called the scattering data. For smooth SU2 monopoles of charge k. And so this is one of the many guises of the Coulomb branch of pure gauge theory. It's kind of well known that it's the same as the moduli space of smooth SU2 monopoles of charge k. And this is just how you explicitly see that in whatever coordinate presentation we were working with. Okay.
So just to clarify a little
Yeah.
bit. So these five L1 to 5K, these are the equivariant parameters.
Yeah.
And the advent description variable for this monopole variables, those are.
Yeah. Yeah. So you would think of the monopole, those variables as like the semi-classical limits of those. Yeah.
For example, if I choose a different mu, say mu equals to 1, 1, and then 0.
Yeah. So okay, if you pick like let's say some series of ones and then some series of zeros, the way this formula changes is, well, you just replace this thing. This thing in that case is the finite dimensional Grassmannian. So when you localize, what happens? The weights in the tangent space, you would now get something like product over J in some subset of 1 to K of size, like however many ones you had, and product over I's in the complementary subset. And you would now get the product of these things in, like, let's say for I in that subset, or however I define it here, or whatever. Yeah, but it's the usual like.
So these are operators related to this equational model.
They're degenerations, yeah. If I did the kind of T star version of everything, and I put and I had some numerator here with the H bar shift, they would literally be the RS Hamiltonian, rational RS Hamiltonian. Yeah. Yeah. Okay. Okay. Any other questions about what I said thus far before we move on? Okay. The main take-home point is that you can trade the difference operator for a space. So it's always better to define things in terms of spaces than some formulas. Okay. Yeah.
Is there a point in mapping P1 into target space?
There's no target here, really. I mean, the P1 you can view as like the one-point compactification of the spatial slice. Yeah. But then we're just doing some problems with bundles on P1 right now. I mean, okay, in some like very tongue-in-cheek way, but bundles on P1 is like maps into BG or something or whatever. Oh no, yeah, of course, right. In general, like if you have some matter, you can introduce extra variables for the matter and whatever. But okay. Okay, so now I'll talk about the application of this stuff. To Quasimaps. And so the general slogan here will be that whatever is our Quasimap stuff is going to arise by coupling the 3D n = 4 theory, let's say G gauge theory, to a boundary theory with G global symmetry. And as I sort of mentioned in the beginning, our friend in the math department, Konstantin, has been a firm advocate of studying these questions. I'll just say up front, like the two main differences in what I am doing from the usual story that is told is, number one, I'm just going to be using Quasimaps. I'm not going to worry about stable maps to general targets. Everything I'm going to do is Quasimap to GIT quotient. And number two, when I get, I'm just talking about pure gauge theory in the talk because it's a nice like running thing to do. But the story should generalize for me to actually more or less arbitrary ADE quiver gauge theories in the bulk, whereas my boundary theory I'm going to think of as more of something fixed instead of general boundary theory. Okay. So in particular, what's the most canonical boundary theory with the G global symmetry? We can look at the sigma model to flag variety. And because I said I wanted to use Quasimap, you want to really view this as the gauge linear sigma model. So actually GLSM. And so what this means concretely is that, like, when G is GLK, the flag variety is the variety of flags. And flags you can parameterize by some quiver. So you can view the flag variety as just arising from this quiver, where you take the quotient by, so mod by kind of all of the circle nodes. And the stability, GIT stability, is that the arrows are injective. Right, so flag variety is just that thing. So now what I want to remind you is that there is a notion of Quasimap to GIT quotient, and you can use that to define the enumerative invariance of this thing. So the basic idea behind Quasimap is whenever you've got like a moduli space of maps from P1 into something that's usually not compact, as I mentioned in the beginning, there are various issues that show up if you try to integrate over it, so you have to define some kind of compactification of naive space of maps. And if the space that you're mapping to happens to be a GIT quotient, and in our example, it's of course a GIT quotient of a vector space by product of GLs. You can think of a holomorphic map to that. It's just a map to the pre-quotient up to gauge transformation. So a Quasimap informally is just defined as a map to the pre-quotient which everywhere lands in the stable locus except for maybe a finite number of points on the base curve. Those are called singularities. And the idea is because you let it slip off the stable locus, like in the quotient description, the non-compactness in moduli of holomorphic maps arises from the fact that you force them to everywhere stay in the stable locus. If you allow them to move off the stable locus at a finite number of points, this will solve your issue. So if I call X my GC mod B, by definition, space of Quasimaps to X is just, and it's always understood that I'm mapping from P1 into X. What is it? Well, it's just a collection of a bunch of vector bundles on the curve. So V1 up to Vk minus 1. Each of these are vector bundles. Their rank is just given by the value of their index. C. And I fix some, for now, fixed trivial rank K bundle W. So the important thing is that these actually vary in moduli, while your bundle for the box is fixed. You don't let it move. And then, just like in the quiver, you have circles in box, and in the moduli you have bundles and sections. So in addition to this, you have to give a stable section, which is just a global section of lowercase holms between all these things. And stable, as I mentioned just informally, just means that viewed as the map on fibers over a point, it's injective except maybe at finitely many points. Okay. And you just look at all that stuff up to just whatever is the natural equivalences. So now, once you've got that, you can define what's called vertex function, which is just the it's in physics terms just the partition function of the GLSM.
Well,
Yeah.
I probably want to say that this theory is arises by some kind of generalization of the boundary condition of the different.
Yeah, I'll get to that after I've. Yeah, so I'll preserve the quiver actually for this reason, but I'll first just say what is the purely 2D computation you'll do. Yeah, so indeed, in the end, we're going to make this all talk to a 3D thing, but for now, I'm just reviewing some kind of reviewing some stuff from 2D or enumerative stuff, whatever. So, yeah.
Like in the different realization of the realization of the space
It definitely affects the space of Quasimaps, yeah. To define the space of Quasimaps as I have, it is with reference to a presentation as a GIT quotient. Like that's as long as everything is like okay, like obviously the part of the moduli spaces where they're actually holomorphic maps are of course all going to be the same, but the kind of stuff you allow on degenerate configurations is sensitive to a quotient presentation. Now, anyway, so some stuff like quantum cohomology just like really doesn't care about the compactification at all. Like even stable map, quasi-map, whatever, it just comes out the same. But anyway, okay. Okay, so what was I saying? Oh, right, I wanted to define vertex function. I should say that like for holomorphic maps, there's a notion of degree. For quasi-map, the degree is just the degree of the bundles considered as a vector. Moreover, there's a open subset inside all quasi-maps called quasi-maps non-singular infinity. And pretty much, this just means that near infinity at P1, they like there's no singularity. Yeah, they actually. Yeah, this was P1. Yeah, that was P1. I mean, of course, the definition of the moduli space actually doesn't care. I mean, you can do it over whatever, but for me, it's P1. Yeah. So it has the evaluation map to the variety at infinity, and well, at 0 it just doesn't, but that just means you have an evaluation map to some quotient stack, where the quotient stack is just whatever. It's just the quotient stack that this thing sits inside of. And so you can define the vertex function. You can view it as a map from, let's say, T times C star epsilon, so equivariant cohomology of the stack into the same thing of the space, except now it's like formal series in some z variables. And so T is just maximal torus inside GOK, which acts there. Okay. And so how do you define this thing? It's easiest to define it with reference to some pairing. So there's a pairing on the cohomology given by just you take alpha and beta. Alpha and beta are inside here. Their pairing is just the integral over the space of the cup.
Sorry, what is the factor?
Oh yeah. So this the flag variety thought of as the GIT quotient for this quiver just sits in, like by saying it's a GIT quotient for a quiver, you're saying like in a fancier language it sits inside of some quotient stack as an open set, and so that's just this one. Yeah. So it's just like this quotient, but just forget the stability. Yeah. I'm going to tell you now. But they're the Kähler, it's just the Kähler variable for G mod B. Just couples to the degrees. So what is vertex function? You can define it by its matrix elements with this pairing. So here gamma is inside of here. you sum over some homology classes. Z's are just whatever couples to them. And then you integrate over the space of Quasimaps, non-singular infinity, going to x of degree beta. So this thing breaks up into the union of finite dimensional components indexed by degrees. You pull back alpha from infinity, and you pull back gamma from 0. And so in principle, you know, like for general targets, to get anything reasonable, you should put virtual class here. But for G mod B, it just turns out that the virtual class is the actual fundamental class. So there's no subtlety. On the level of localization formula, it means you have all denominators, no numerator. Yeah, well, just to have any kind of like reasonable answers, or you know, like any just reasonably well-defined enumerative problem, you have to be integrating against a virtual class or working with the virtual structure sheaf or something. But because the flag is really nice, it just turns out the virtual class is the actual class. There's no funny business. Okay. Okay, so that's vertex function. And so explicitly, what is this thing? It's just some really complicated function of like a bunch of variables, right? Because it depends on z variables. All integrals are taken equivariantly, so this is going to depend in addition on some equivariant variables like epsilon for the loop rotation, as well as like some variables associated to GLK acting here. So in particular, it will be a function of I can write z, oh, sorry. We can think of vertex as like function of a whole bunch of stuff. It's a function of like z, it's a function of phi's, it's a function of epsilon. And what I had just told you previously was like, if you just give me any function, you know, symmetric function of some variables, and so maybe I should have written GLK here or something. Symmetric function of some variables. There were some nice difference operators I could make act on it that I could then give a geometric interpretation. Yeah. So you can just make them act on the vertex function, viewed as a function of those variables. But the point is that you can actually give geometric meaning to this, and it has to do with this picture of coupling the bulk gauge theory to some boundary theory. So in terms of pictures, what this does, so I can, maybe I don't want to erase that. In terms of pictures, what this does is it says, well now, in whatever was my 3D space-time before, which I was drawing vertically, so I'll keep doing that, I had the t equals 0 slice, I had the t equals 1 slice, and instead of just taking the Neumann boundary condition there on gauge fields and everything else, I can consider coupling it to some 2D boundary theory. Yeah, so t equals 1 gets preferred because that's where I can canonically couple to 2D boundary theory. On the Dirichlet boundary, you can't do stuff like that. Now the point is that I told you previously, like, if you put nothing in the bulk, the localization locus is just a point in the 3D bulk. So it's, I won't like go into any details, but like it's believable that therefore if you just have some 2D theory there, localizing this will just reduce you to whatever the computation of the 2D theory was, because everything's happening here. So now what we want to do is we want to consider this type of configuration, but where we now actually insert something in 3D. And so what you can do is put Dirac singularity of charge mu, which again is some minuscule co-character, which think of as minuscule co-character for the GL. And now you ask, well, what does it mean to localize this thing? Well, given all of the preparations, hopefully it's kind of yeah. Nothing. Like you would just go back to the 2D computation because there's no dynamics here. Like there's no dynamics here. Like without any insertion here, the localization equations just force there to be like no evolution here at all. So everything here gets killed, and you just keep whatever you had in 2D. So no insertion, you would just literally compute the vertex function essentially. Now I'm going to ask, what if I do a 3D insertion? That's the main thing.
Without insertion, you compute the vertex bound with the vertex function.
Yeah, so no insertion. And I'm skipping like several details, but like that's essentially true. Okay, given all the preparations, it's probably easy to guess what is going to happen if you put the Dirac singularity of charge mu here. It just means, well, the framing bundle, which you had previously thought of as being fixed and trivial, since this thing is really the UK gauge theory in the bulk, you now, I'll just write the superscript mu on it. Instead of considering it to be fixed and trivial, you consider it to be related to the trivial bundle by the Heck modification of type mu. And likewise, like I'll just call the moduli of Quasimaps with that kind of a thing QM mu. So you're just enlarging your moduli space by whatever data was associated to the variation of the bundle before. So clearly, if X is the point, and we just have no boundary theory, this recovers exactly what we had done in the beginning. And now I'm just telling you, well, if you're coupling to some kind of boundary GLSM, what you do is in your moduli of Quasimaps, you just allow the framing bundles to vary in moduli, but somehow only a little bit. Because in principle, you can consider the whole bun G worth of variations of them, but if you just do this kind of setup and put a single Dirac charge, they just vary in a finite dimensional space. Okay. And so clearly this thing projects to Gur mu just by forgetting everything except the data of that modification. And so you can define, just copy and paste everything. You can.
So the superscript mu means that now WK.
Yeah, it means that instead of W being fixed and trivial, it's related to the trivial bundle by a Heck modification of a prescribed type. So it varies in some finite dimensional space.
The modification is at 20 or 0?
0. Clearly, if you were on higher genus curve, you could, if you wouldn't work equivariantly, and you could do this, but just have it modified at any point. This would be fine. It would be defined. Computing with it might be hard, but it's defined.
One question is how do I think about boundary condition? Previously, we introduced the minor boundary condition. Why did you make that choice?
Why did I make that choice? Well, essentially well, the honest original motivation was because it made the calculation very easy. It gives you something very computable. That's the short version. And now what I'm saying is, given that we've understood in great detail the very simple, very computable thing, let's start playing games with it to do complicated stuff. And then, of course, also the section now is, of course, a section of the modified bundle. Okay, so now the point is, this moduli of Quasimaps, and hopefully you'll still be able to see it. You can just copy and paste everything from vertex function and put the superscript mu on everything. So you have now a priori another vertex function shifted by mu or something. And in addition, I have some freedom, I have some new class of insertions I can make, because since the moduli space has this projection to Gur mu, in addition, inside of here, I can consider inserting classes that are just pulled back from there, which will be all like Chern polynomials with some tautological stuff. So that's on Gur mu. Okay. So I'll try to erase everything except the important part of this board. Okay. So far, all I've done is I've just defined some cousin of the vertex labeled by mu by just integration over some other space. Now, what you can do, so now I'll just say easy localization. Argument tells you that after adjusting the normalization, on the vertex mu, so it's not very informative to write explicitly what it is, but essentially it's like you have to multiply by some kind of monomial in z's, and you have to multiply by these gamma class or Iritani class prefactors. So if you know what Iritani class is, you probably already know what I mean. If you don't, it's just it's just a more convenient normalization to work with for this thing. Vertex mu is actually equal to the original vertex acted on by explicit difference operator in phi i's, where the difference operator is just the one I wrote essentially earlier in the talk. So this is the maybe I'll say a few more words about geometrically what this actually means. What you're basically doing is you're saying instead of just counting maps from the base into G mod B, you're saying now I'm actually counting sections of a G mod B bundle over P1, where the bundle is twisted in some way. And so in the kind of case where this was done before, where it's mostly done by like Okunkov or Okunkov-Padre-Pande, whatever, they always consider just twisting by a torus in the flavor symmetries. And so when you twist by a torus in the flavor symmetry, like a co-character into a torus just uniquely defines for you a T bundle over P1 by just essentially making it the transistor function. And so then what you can do is you can define shift operator on in some theory of maps by just instead of counting maps of the trivial bundle, you just count sections of some bundle twisted up by this co-character. Now the basic puzzle is that if you have actually non-abelian group of symmetries and you want to make use of it, the co-character the co-character into the non-abelian group does not define for you uniquely any kind of G bundle over P1 anymore. But the claim is that you should just do kind of the simplest thing possible. You could say, well, while the co-character doesn't define for you the bundle uniquely, it does give you a finite dimensional family of bundles. And so what you should do is in some sense just choose. In some sense, you should just choose all of them and then integrate over the space of choice. So that's all this says. No. I'm just saying, like, if you have a like non-abelian, like GLN, okay, a co-character into GLN does not uniquely specify a GLN bundle on P1. It specifies a family of GLN bundles, which is finite dimensional, but not a single one. By contrast, a co-character into a torus really does. give you a single one. And I'm just saying you can view the fact that you have to enlarge the moduli space as just a consequence of the fact that that bundle is not unique. So you just average over the choices. Exactly. If you wanted some, yeah. That's a nonabelian generalization. Exactly. Yeah. And so, yeah.
Co-character into some group, you use that to build a bundle as a collection function.
Yeah. And I'm just saying, if you have a co-character into a torus, you can just just from that data, it's the same as the data to build a clutching function. Because if your co-character is just a bunch of integers, you just do like z to those integers, and that's your clutching function. Whereas in the non-abelian group, it's just not true. That like you have the wild group and whatever, and there's no uniquely defined bundle on P1 for any co-character, but there is a uniquely defined orbit in the affine Grassmannian for a given co-character. Yeah. Yeah. Oh, exactly. The kind of shift I want to get. So if I want to, you could in principle consider this as a family over the whole affine Grassmannian, but if you want to get a shift operator which acts just at some finite order of translation in the variables, you've got to restrict to a cell. Yeah. Like the thing I wrote before was basically a linear combination of shifts in individual variables by one unit. And so more generally, if you localize against some other mu, you're just going to get a whole bunch of shifts in all variables. So varying over the whole affine Grassmannian tells you you can in principle consider all possible shifts by anything, but usually you want to just look at some minuscule smallest thing as the basic shift. Yeah, exactly right. So you can go and go and go, but yeah, but you want it to get nice stuff. Yeah, in type A, in type A, indeed. Yeah.
So in this sandwich feature on the upper board, you have this T+0, let's call that the Dirichlet boundary condition. So if I sandwich two Dirichlet boundary condition with drag similarity in between, is that the Coulomb branch? I'm trying to insert the third slice in the middle to understand what you're doing.
Well, the Coulomb branch itself, or at least the algebra of functions on the Coulomb branch, is just determined by the algebra of observables in the bulk, right? It's just basically how it's defined in this way. Yeah. So what I'm saying, so the thing is, by locality, the algebra of observables in the bulk doesn't care which boundary conditions I compute with. So I can choose a nice set of them in order to facilitate computation. That's the philosophy. Okay. Yep.
So it looks like for every point in the affine Grassmannian, you have some sort of ordinal count, right?
Sure.
When you write that it depends only on the Schubert cell, do you mean that you can just identify this curve count for the whole Schubert cell, or you just somehow integrate over the whole Schubert cell?
Yeah, no, I mean the integrate.
Integrate.
What I mean is I enlarge actually my space of Quasimaps. So there's two distinct things you could consider doing. So thing number one is you could, right.
Or somehow integrate with the base.
Exactly.
You push forward for the base and then
yeah.
you are push forward into the base.
Yeah. I'm integrating over that as part of the definition. Yeah.
Your things your own here in.
Yeah. Right. But the fiber should be interesting. But I'll come back at the end. Yeah.
Is there anything nice about push forward itself before you integrate, or?
I mean, it seems to be about as nice as a Quasimap count is in general. So it's whatever. It's about as non-localized as the original vertex function is. The nicest push forward that happens here is actually when you push all the way down to the point. because what this tells you is that,
yeah, but like,
yeah.
maybe you want to keep some intermediate data, which is richer. Like, if you push forward to actual intermediate step and like see how.
Yeah. So at the end, yeah, I believe actually just this push forward, without going all the way down, should be pretty interesting. But I'll wait till the end to say what I think is the. I haven't done the computation, but there's a. Okay, I'll just say it now. The vertex functions are the direct number theoretic, or the direct analogs in number theory of the Eisenstein series. And Eisenstein series depend on two kinds of arguments. So one is just like direct analog of the z variables, but the second argument in Eisenstein series is actually the direct analog of considering a fiber in such a family over the whole Bun-G. So if you want to have some dictionary between the number theoretic and geometric Langlands, it suggests that you should consider like the fibers of that as the direct analogs of the Eisenstein series at some anyway. But I'll leave that for okay. But main point is, for now, if you're just interested in analogs of difference operators that actually make use of nonabelian symmetry, it's good enough just to push forward all the way down to the point, integrate over everything. Okay. Okay, so now what we're actually going to do with this is basically the main question, and I'm almost out of time, but, well, I guess there's no actual time, but people probably have to go. So the main thing is that, like, usually when you define shift operator, the idea is that you want to somehow, with a few extra steps, you can show that the geometric definition of the shift operator also implies that the vertex function satisfies some nice difference equation, and then you want to try to get that difference equation into a standard form. And so the exact analog of that argument, in this context, I actually don't know, but I'll tell you something that I know that does work, that amounts to a different way to characterize the quantum differential equation and epsilon difference equations of this thing. And so, of course, it goes without saying that quantum cohomology of G mod B is like older than me, so we're certainly not going to learn anything that people haven't already said about quantum cohomology and quantum demodule of G mod B, but it will interact in an interesting way with Coulomb branches, as again Telemann has pointed out several times. And what I'll say today actually has a generalization to like arbitrary 3D Coulomb branches instead of just the ones with pure gauge theory. Or at least arbitrary ADE, affine ADE quivers. Okay. So what is basically the idea that you want to follow? Here, it's this boundary. So there's something kind of asymmetric about doing the coupled bulk boundary system when the boundary theory itself has gauge groups. Because there's something, some gauge groups live only somehow at the t=1 boundary, and other gauge groups live on some bulk slices. So we would like to use basically this, what did I say, 3? We'd like to use the fact that we have some boundary gauge groups to kind of decompose this boundary condition into a sequence of simpler things. And the way that this works is it means, I'll just say the answer, I'll just draw some pictures. So I've been drawing all of my pictures vertically in the time direction. I'm going to switch to horizontal so that I don't break my eyes. So if t=0 is now over here, and t=1 is now somewhere over here, what we say is like, okay, I've got some stuff, and now I make actually a bunch of interfaces. So I start with the pure UK gauge theory here. I put the pure UK -1 gauge theory here, and so on. I'll draw like this. Until you get down to the pure U1 gauge theory at the last step. And at the interfaces, the way you define them is you just say that there's some bifundamental chiral sitting at any given interface, or bifundamental with respect to the gauge groups on the left and the right, and it's just minimally coupled to each thing. So this tells us how each Coulomb branch talks to each other. So in particular, these are all Neumann boundary conditions deformed by these chirals, and this is my favorite Dirichlet boundary condition, where I fixed this stuff, which are like my equivariant variables for the G symmetry. Now, the point is that when you present things this way, it's clear that all of the insertions I just defined actually generalize to allowing any insertion of a bulk Coulomb branch observable in any of the intervals between two bifundamentals. And so what this means in terms of like precise math is that I can define a whole bunch of families of the Quasimap spaces where, like, if I insert, so if I'm in some region where there's the uj gauge group and then I have the uj plus 1 on the other side, if I want to insert, for example, I'll draw all three actually. If I want to insert some Dirac singularity with charge nu j, charge of monopole, how does it define, so as I've said, like basically ad nauseum in this talk by now, every time you make an insertion like that, its job is always to modify the localization locus, right? Like the space that you're integrating over. So how does it modify it now? Well, it's like if I had Quasimaps, nu j, it would be like all the same data, and the only thing that changes is that when I look at which bundle I have section of, I have something like columns from nu j minus 1 into now nu j twisted by Hecke modification of that type, plus everything else normal. So like what goes in here is just like the usual moduli of bundles, and now I get just some extra moduli associated to this Hecke modification, just like before. And so you can define analogs of the vertex function by just integrating over that, and I will call them all in some suggestive notation, like expectation value of u nu j x, where this is some generating parameter for tautological stuff, as it always is. Okay. And maybe if nu j is like, I don't know, fundamental, or like the fundamental, so 1, 0, 0, where this is now the j component, I'll just call this thing by u plus j, something like that. Okay, so now in order to wrap this up, I'll just say, what is the punchline? Oh, and sorry, one more thing. One more piece of notation is I just define q sub j, expectation value of q sub j, to be a vertex with a descendant insertion which was just like the pullback of stuff. Like in this here, it's just whatever gamma is, the pullback of some stuff from the stack. Given by the Chern polynomial of like my, maybe the dual of the fiber of Vj over 0. This usual thing. So now, why do we care about this? Yeah.
So when you insert, for example, very early on, you insert some polynomial like I1, like K, and also this the logical class. I think they are inserted on the 0 or 1.
All my insertions happen at 0, yeah. Okay, so what is the point? So the point is that you can show, by direct analysis, and it's a very short analysis, like one line of work, of the localization measure, localization weights, that basically Q j plus 1, there's some kind of identity satisfied by all these things, and I'll explain kind of where it comes from in a second. So it's just some recursion relation that tells you what is Q and U at the j plus 1 step if you somehow know them at the previous step. So why should such a relation like that exist? Well, as I explained before, U's and Q's were really like their coefficients in X were really like the functions on the Coulomb branch of whatever my bulk, of whatever my bulk gauge theory was. And when you flow it to low energies and you have some kind of setup like this, you expect that like interfaces between two such blocks like that are going to actually correspond to like Lagrangian correspondences between, like, let's say the j plus 1 and the j Coulomb branch. And so explicitly, those Lagrangian correspondences, if you're sort of lucky, it will be cut out by some nice equations, which can be recorded as relations among the functions on both sides. And this is just what they are in this case. Okay. No, fiber over 0. So remember, Vj plus 1 is the bundle on the curve, and I have moduli bundles, so I can take the universal bundle, take the... Oh God, sorry, yeah, yeah, sorry. Curly, yeah, so Calvi and Nu are the same in handwriting. But now you see this is some kind of a very simple recursion relation, and moreover, it's actually even simpler because what are these observables? They're just first Chern class of tautological, but this is basically exactly what couples to degree, right? So it means that you can essentially trade this for a derivative in Z variables. So it's just you just find this by computation, but it's just because, remember, like the coordinates on the Coulomb branch, the generators of the Coulomb branch ring are just essentially the coefficients of like Q and U's, right? And so if you want to get some describe on the level of coordinate rings Lagrangian correspondence between the two Coulomb branches, it's just some relation on the coordinates on either side, right? And I'm just asserting that it actually like the one defined by this bifundamental chiral interface takes a very simple form. It's just this thing. Yeah.
You would have gotten a nice formula.
Oh, totally. Like I could have done bigger jumps and still gotten a reasonable formula for sure. Now, if I didn't put a bifundamental chiral and I put something totally insane, then I don't know. But right. No, the jumping is not a huge deal. But for what I want to say, it will be convenient to always just do jumps by one. Okay. So anyway, the point is here, you've just got insertions of C1 tautological, right? And this is just exactly what couples to Z variables. So then by picking some appropriate coordinates some indexing of your z variables, you can trade this thing for actually some differential operator. In Kähler variables acting on that expectation value. And so now, what can we do? Well, it's clear that we can do some, oh God, sorry. We can do some kind of induction. So induction will now tell you that if you have, we can just write it as a matrix equation. If you have qk, uk, this will be x minus epsilon zk dd zk, zk minus zk minus 1, 0, all the way to the bottom. And now, well, Q0 and U0. But now remember, U0 is the polynomial of degree at most -1. So, 0. And Q0 is monic of degree 0. So this is just the expectation of 1, better known as vertex itself. Moreover, what was this? Well, QK was just generating polynomial and actually just equivariant variables for the framing bundle. So it's just, it pulls out of the expectation value. It's a constant. So this is just the number, I'll say vertex times this number. Yeah, so remember I had Kähler variables z, and I was pretty inexplicit about any actual like choice of basis for them or anything. And now I'm just saying like I can pick some basis so that this is true. So it's just the j+1 component of z, that basis.
If you flag for GLK, like for GLK minus 1, you're thinking they are all related?
No, I have only one space. I'm just in flag for GLK. But the flag for GLK just has many Kähler moduli. It has one for each node.
Right.
Yeah. I'm just picking some parameterization.
And for this X, these are variables for which group?
X is just generating from this point of view, it's just auxiliary. It just records coefficient. Like you just take coefficients of stuff in X. Yeah. And now, as I explained, the expectation of U plus sub k would be the actual explicit operator, difference operator, the nonabelian version of shift operator acting on vertex. But now, what is this? So the matrices entering this equation, which we've essentially read off from here, are actually the 2x2 Lax matrix for the open Toda chain. And it is, as I said, a result older than me that in fact the vertex function of the flag variety is the eigenfunction for the Toda lattice. And here you just get it as like the top component in some matrix equation, right? Because if the meaning of this statement essentially boils down to the fact that like if you just work this matrix multiplication out, the top left entry in the whole thing is the generating function with the Toda Hamiltonians. So when you act on this vector, you get exactly the eigenvalue condition here, the eigenvector condition there. And likewise, you can view then the second row of this equation as the explicit characterization of the difference equation obeyed by the vertex function of GLK mod B in terms of the same Toda lattice description. So I should mention, huh? Oh, I'm just saying like, what is the left-hand side of the second equation? It's just the vertex function acted on by the nonabelian shift operator. And I'm just saying, like, then the right-hand side of this equation is just tells you what that is in terms of the total lattice. And so I should mention that, like, importantly, this thing satisfies the RTT equals TTR, where R is the usual Yangian SL2 R matrix. And this is a very short computation. And then it's automatic, given that by the standard kind of train track argument, that this whole thing satisfies RTT equals TTR for Yangian SL2 R matrix. And of course, it's also expected or known, or it's proven, that the quantized Coulomb branches are indeed truncations of shifted shifted quantum groups. And so this is how you see very explicitly that realization in this language. Yeah.
Actually, this is two different last measures.
Indeed.
One of them 2 by 2, and the other n by n.
Yeah.
And you observe the second one.
I think you can using bow variety, but I haven't done it yet. I think you can, but I like the 2 by 2 one for this step. So then, just very quickly, like closing thoughts. So one is that this generalizes to arbitrary, possibly affine, ADE bulk quiver. Boundary theory will just be now will be, well, something you know, but a cousin of the flag, some cousin of flag variety. Maybe if people are very brave with, like Malako-Kunkov Yangians, you can try to get some statement on any quiver, but I won't do that. And yeah, thought number 2 is that this, like the nonabelian shift is the direct geometric Langlands analog. There's some statement. I don't know if it's a statement that leads to anything
so you'll get
nice.
interesting statements for a set of very special boundary theories.
That's, yeah, like, so the usual way people want to do this is consider the most general class of boundary theories that they can, and look maybe just at the pure gauge theory Coulomb branch. I believe one should kind of invert this logic and look at only boundary theories that are close to G mod B, but do it for any Coulomb branch. Then what you'll find is a whole bunch of nice parameterizations of the Coulomb branch that generalize this. And as I mentioned earlier, the nonabelian shift is basically the direct geometric Langlands analog of the action of, like, the classical Heck operators on Eisenstein series. In the number field setting. And I have more thoughts, but I won't say them while anything's recording. That's all I have. So thank you to those who lasted the whole time. I'm sorry.
More questions?
Yeah.
I should have maybe asked this earlier, but you had the map pi mu going from Quasimap mu to Go mu.
Yeah.
What does that actually project down? Does it just project out
It just forgets all data except the Heca modification of the trivia bundle.
Hit a point in going to then? Like,
No. So Quasimaps really is the union of infinitely many components over all degrees, and that map is, I think, surjective on components of high enough degree. I mean, you're correct that like one should always be like a little bit careful writing the maps like that, because Heca modifying the bundle does change its ability to have sections, or like so you got to be careful. But basically, because I was looking at not sections of just that bundle, but homes of something variable into that bundle, I can always just turn the crank on the variable thing to make sure it's I don't do anything bad.
Question.
Yeah.
So you realize that the flag variety has the Higgs branch of some figure.
Yeah.
But then you put in this picture, everyone is like in a very uniform picture. You say U1,
Yeah, I promoted everybody to 3D gauge groups, so they're all kind of on the same footing. Yeah.
And then how should I understand? Like you put the first MS1 slab you do Higgs branch on those guys, and the last one you do a Coulomb branch.
No, I do Higgs, like the theory is just the theory, and then just the way I cook up the boundary conditions and couplings and stuff ensures that when I make the sandwich, like all of those together form the 2D sigma model into the flag variety. And then in fact, sandwiching with the last thing basically kills the 3D gauge group. It just collapses it down to some very basic finite dimensional integral, which gave the action of the shift operator on the vertex. That's how it works. So somehow they're just all 3D gauge theories. I mean, this is like something in the UV, so you don't even have to make reference to Coulomb phase, Higgs phase, whatever. They just all exist as 3D gauge theories. And then when you make this sandwich, you just compute something, and the thing you compute is what I defined, essentially. Yeah.
So you're saying instead of geometry, you're trying to say that this 3D theory somehow is quantum theory.
Yeah, I haven't thought of it.
What is the relation between this 3D theory? The same where these shift operators are?
Yeah, so this is actually something I don't really know. So let me put it like this. So in the number field setting, many things get very complicated in the number field setting. One thing that is actually, like the one thing that's actually easier in the number field setting than geometric setting is the actual definition of Heca operator. Because in the number field setting, like, you're just looking at like basically functions on Bungie, and the Heca operator is just some explicit like thing that acts on one of the arguments. Whereas in the geometric context, you have to define it as like the convolution by some IC sheaf or whatever. And so what I'm saying is that like there's a very literal dictionary without even making reference to like the Kapustin-Witten twist, or like I don't need to know anything fancy about geometric language at all. There's a very literal dictionary between these like curve counting functions with targets G mod B's and like Eisenstein series in number theory, because the Eisenstein series are essentially some rational point counts of flag varieties. And just under that dictionary, basically by just replacing the base curve of your counts by like spec Z or something, the Heca operator in the number field context is just literally gets identified with this type of thing I was defining here. Now what I said, to make this like really sharp, you would need to do what Yvonne was asking me about, which is instead of just pushing down all the way to the point, you should actually you should remember actually what's going on with the counts in the fibers. And I am like very interested in doing something like this, but it's right. Yes and no. I mean, like I see what you're saying, because like to get from 4D to 3D, like obviously there's some, but yeah, but I'm still using somehow the like. I just here define them on the level of like some numerical computations. I could have like taken a fiber of the family, viewed as something living over bungee, and then done heck modifications on that level. And I think that would be more like the honest thing. Here I just took the fiber over. I looked at what was going on at the fiber over one point because it's already interesting. But in principle, you can do other things. Yeah.
So during the 3D block theory, you have a surrogate, two surrogates.
Yeah.
And then on the boundary, put 2D sigma model with some kind of vector.
Yeah.
What if in the problem have a junction?
Yeah.
What in general?
Yeah, so this is what we're working out with Sujay and Mina basically is and probably some vector bundle over flag variety. But you replace G mod B by a very close cousin of it, which is just combinatorially determined by which matter you put, as long as you're doing AD. Well, actually, for literally something that lives over G mod B, just A1 quiver. If you do KN, then you replace G mod B by like maybe a vector bundle over it, determined by what is N. And then the analogous statement would be that essentially this factorization that you see here would get replaced by, like the building blocks would no longer be these things, but they would be some other 2x2 matrices that are explicit functions of like the Kähler variables of the boundary theory. And it would realize what's called multiplication map for a slice of an affine correspondent.
Okay, there's no other questions. Let's thank the speaker again.
You had some further comments you wanted to make offline.
Oh.